enough to give me a project to work on for senior design. And I'm going to be talking to you today about force structure analysis. So I'm going to start with a little overview of the company and the project, and then we're going to move through to the analysis of the problem at hand. And then we're going to take a look at the model that I used to try to figure out some of the pieces of force structure analysis. Then we'll look at the analysis and interpretation, and then we'll take a look at the applications that models like this can be used for. So again, I'm going to start with an overview. Lockheed Martin is a defense contractor for the United States as well as international governments. And they have several business units across the United States, including Lockheed Martin International as well as space and all kinds of business technology. But the group that I've been working for is Lockheed Martin Aeronautics, which is headquartered in Fort Worth, Texas. And they are in charge of all kinds of advanced development programs as well as the fighter programs and also the heavy programs such as the C-130 and some of the P-3 stuff as well. But when we started working with Lockheed on something that we could do for OR, the first thing that came up that was really beneficial and that could be broken apart and kind of applied to our degree was force structure analysis. And force structure analysis, kind of in a nutshell, is taking stuff and looking at the resources and looking how those resources can be cost effectively applied to a business situation or in the military situation, how can that be applied in a strategic sense. And actually, most people know that military engineering was the first type of engineering, and it was kind of what OR morphed into. And what it started back in the early wars as was what's the quickest way to get to our enemy and what's the best way to take them over. But when we look at force structure analysis in today's world, and we look at military strategy using OR, some of the things that we consider from an aerospace standpoint is which aircraft are we going to send to which target, and what kind of weapons are we going to be loading onto that aircraft. So this can be used in all types of situations. Up here I have two pictures of Lockheed's aircraft. This isn't particular to this project. It's noteworthy to mention that. But they are two aircraft that are both produced by Lockheed. This can be used for sales pitches and teaching the customers what they will be gaining when they purchase a new aircraft. But also force structure analysis can be used with current inventory and to decide how you're going to apply the inventory and resources that you already have. So why does it matter? Many of you are probably thinking, I'm not military, I have no desire to go into defense. Why does it matter? Well, so there's a dollar sign attached to it, so that's why it matters. Everybody cares about that, and your tax dollars certainly go towards the defense budget. So the dollar sign that we see attached is the difference in a day of using a fighter jet can make the difference in 12 to 15 grand per sortie that's operated. And I'll kind of explain a little bit further in detail what a sortie is in a little bit. But there's some money that can be saved by scaling back on the days that we operate in a combat sense. The biggest thing, though, and one of the biggest things to Lockheed is their motto is we never forget who we're working for. And so there's the people side of this as well. Today, the U.S. military is operating in many hostile war environments, and there's the decreased risk of aircraft loss by operating a little bit smarter and pulling back on combat days, as well as the decreased risk of human loss. So I'm sure most of us know somebody, a family member or friend who has served in the military, and it's certainly beneficial to decrease the risk for them going out on the front lines. So I'm going to be taking a look at the problem that I was given, and this is kind of a Reader's Digest version of the force structure analysis problem. And I'll explain a little bit more on why, because these problems typically have thousands and thousands of variables, accompanied by thousands of constraints. And these constraints and variables can also vary between decision makers. So these force structure analysis methods are usually used in the decision-making process for acquisition or combat strategy. And when you get several four-star generals in a room, they're often going to disagree on what the most important variable is. And so there's going to be different values placed on stuff. So the problem that I was given was a really small, scaled-down problem where we took a look at 4 aircraft type, 4 weapon types, and 4 target types. And these are all listed in increasing order of power or effectiveness on the slide. But what we essentially are going to be doing is applying a certain type of aircraft, choosing a weapon set for it, or a weapon loadout, as we call it, and then sending it towards a target type. And you're going to have constraints along the way that are going to help you decide where those weapons should go and how they should be accomplishing the task that they should. But the big challenge for this is how do we get all these objectives integrated? And again, it kind of goes back to everybody weights some of the variables differently, and it's tough to get everybody to work together, and it's tough to get the variables in the program to work together. And once you start getting it into the program, and we use GANs in this situation, are the results even realistic? Sometimes you start to break them apart, and it doesn't even make sense for the context of the problem. So, and you're going to see runtime be affected as well, just because of the nature of it having so many variables and constraints. But the biggest piece as well is balanced resource allocation. Once you start to see the sorties be broken down and be applied, and have certain aircraft going to a certain target with a certain weapon set, you want to make sure that all the aircraft in your inventory are being equally used, and you don't have some that are just sitting dormant. But you also want to make sure that the resources are being used to the best of their ability. So if you have a really large jet, for example, with a really large bomb, you wouldn't want to send it to one of your smaller targets. So you want to make sure that there's some sense and some logic behind why the aircraft is being sent to the target it is and with what weapon. So I'm going to go into a little bit of the description of the model. In this case, we chose to use GANs, and we approached this as a mixed integer program. The reason for that being, again, this all kind of revolves around decision makers, and it's really hard to tell a decision maker to fly half of a jet to a quarter of a target and to drop half of a bomb. So that's why we use the mixed integer program. It forces some of those necessity variables to come out as a whole number, which is a lot easier to give a business or strategy suggestion. So there were 514 variables and only 114 constraints in this problem. This was extremely scaled back from what a normal force structure analysis problem would look like. One of the pieces that we tried in this problem as well, with little success, was to do a mixed and multiple objective function. So I worked through some iterations with Dr. Barr, and we looked at doing the multiple objective function, and in the end kind of came back to using one of the original single objective functions, and we'll talk some more about that in this slide. So the constraints that are really driving what gets sent where with what weapon is going to be available sorties. So a sortie class is when you have that specific unique set of an aircraft, a weapon, and a target. And you'll only have a certain number of available sorties given on the number of available aircraft that you have. You also have the expected kill per sortie that is going to be driving how much effectiveness that aircraft and that sortie has. But that's also going to be scaled back and driven by requirements that are given to you by the combat situation on how many targets should be taken out or required to be taken out in order for the sortie to be a success and for the campaign to be a success. So the campaign is going to refer to a set of sorties over a given amount of days. And the other thing that's going to constrain you a bit is resource constraints. So such as the weapons and the aircraft, you don't want to be able to draw from an unlimited resource pile. And that's just to make sure that everything is realistic, but it also affects how your resources begin to be applied to the problem. If you have an unlimited resource set, then you start to see things be applied not to the best of their ability. So the optimization that we ended up falling back on was to look at the days in the campaign and attempt to minimize that. And the way that we did this was to run several iterations, and we started with 10 days, just as all the data was scaled down really small, so we could look at it on a really small scale, such as the 10-day, rather than a large 130-day combat schedule. So when we first ran it on 10 days, what you see is that you get a success. But what we'll talk about a little bit later when we go through the analysis of the results is that you have to end up running a binary search and rerunning all of this program to see where the success and the failure starts to converge on each other. And so we'll talk about that a little bit later. But the second thing that you can do is use goal programming, and then you want to minimize the deviation from the required targets that you're to hit in your combat situation. So we'll look at some of the results from that binary search iteration that I was talking about a second ago. And when you start doing this binary cut, what you see that first time that I was talking about, you run it 10 days, it's a success. Your campaign is a success. You met all of the targets that you were required to hit. So in that binary search, you go down to half that value immediately. And at 5 days, it's a failure. So So you know now that that sweet spot of where the less amount of days, the least amount of days that you can still succeed is somewhere between 5 and 10. So if you continue that binary search, you go up to 8 and see it's a success, 7 is a failure. And since this is a mixed integer program, we know that 8 is the minimum amount of days required to complete this campaign successfully. So from all of that data and running several iterations, we can get a graph that looks like this. And this is basically telling us that your chances of success and your percentage of targets hit and your percentage of success overall in the campaign exponentially increases as you increase the time in the campaign. But this kind of gets sticky because it goes back to, well, what's the value on adding a day to the campaign? There's a monetary cost, but there's also a risk associated with human life and aircraft life. And different generals and different decision makers in acquisition will also make vastly different decisions on the risk profile that they're willing to take. So with a little bit more manipulation, you can see this efficiency frontier, and this gives you a little bit more of an idea of the trade-off that you're making. So again, you see yourself start to move up in the days in campaign, and the lower the days in campaign, there's a higher chance that you miss your target. So again, the big application for all of these programs, and most of them are a lot bigger and companies with a lot more variables and situations. But the big place for this is acquisition, and you'll see it in fleet comparisons, oftentimes between contractors, but sometimes within the contractor internally as well. But combat analysis and planning is a huge place that you'll see this on the battlefield. How are we going to apply the resources that we already have? So force structure and size is another thing. If we've already decided to purchase aircraft, how many do we need to be effective on the combat field? And it all goes back to different decision makers are going to make different variables of higher value, and that's what you kind of start to run into with the problems with having a weighted objective, mixed objective. When you start to weight things, it all depends on who's making the decision on whether or not it's accurate. So to wrap up, we kind of went through a really, really quick run through of what force structure analysis is, what the problem that I dealt with, this Reader's Digest version, if you will, of the force structure analysis, what it looks like and what the model looks like in GAMS. And then we took a look at the analysis interpretation of the results and looked at some of the applications in industry and how these programs are helping to save money. So the next time that you see on the news arguments or discussions about how the defense budget is being used or whether or not we're using our resources to the full ability that we have, you can think that there actually is a math model behind this, and there is some madness to the methods. So I'll open it up to any questions, and thank you guys for sitting through this.
You tell us how many variables and constraints. Tell us about how many planes and targets and all were involved in that in your case study.
So in the case study, it was scaled down significantly smaller than what real life would be. The fleet that we had of the most advanced jet was at 3, only 3 jets in the entire inventory, and then you jumped up to 5 and 10.
Said about 20.
Yeah, 20 to 25 planes in the entire military force, but
How many targets do you remember
there were 100 targets total. So, and that was split 40, 30, 20, 10, and increasing difficulty to achieve.
So that's what turned into that model of the 115 constraints and so many variables.
Yes.
How long did it take to solve that?
It actually was quick. When it got slow was when you started to increase the fleet size, which I guess is expected, and then also when